comes the value of H.
Why stop roasting us?
What? 99 is
I'll just only show one on that makes it count.
He's covering the astro this almost the green layer side. It's close to each other, but they're not the same. Double the astro. And here, because I've got this shattered.
Just throw it and it's
Rotation.
Just a moment, please. My name is Margaret Baggio. I'm the Program Manager for Education and Outreach for NASA's Texas Space Grant Consortium and the PI for the STEM Enhancement in Earth Science Project, which all of these students have participated in for longer than 2 weeks. So they have actually been working remote for almost 60 hours prior to coming to the University of Texas at Austin. And they've been housed here working with NASA scientists and engineers, analyzing Earth-observing satellite data and developing project mission plans for other NASA themes. So we're really pleased that all of these students were able to have this opportunity. We believe that they are the next generation of explorers. I would like to remind everyone to silence their phones. We'd like to make sure that we're giving the students the same respect that they have been giving us the last couple of weeks. They worked really hard. Some of them have been very frustrated, and I believe that frustration only allows you to learn and develop as an individual. If you're not frustrated, you're kind of coasting along. So I think these students probably will tell you that they have learned a lot in the amount of time that they have been here. Our first project today is the Aerospace Engineering Group. So if y'all want to come forward and get ready for your presentation.
Good afternoon and thank you for being here. We are the Aerospace Engineering team and our project was an Iridium Prime satellite payload called Cosmos. I'm Pauline Umansky and I'm from Pleasanton, California.
My name is Cameron Behar. I'm from Miami, Florida.
I'm Leonard Mood. I'm from Chicago, Illinois.
I'm Brianna Cueto and I'm from Round Rock, Texas.
My name is Sheikh Gadi. I'm from Boise, Idaho.
And I'm Diana myself from Houston, Texas.
So Iridium is a constellation of satellites that was created by Motorola in the 80s and 90s with intent of creating a global communication network. Originally, Motorola thought that they would need 77 satellites for this purpose, which is why they named their project Iridium after the 77th element of the periodic table. However, they found out that they only needed 66 satellites, which they placed in 6 orbital planes with 11 satellites per orbital plane. Right now, Iridium is updating the systems because their satellites are pretty old since they've been up there since the 90s. And Iridium Next is currently being launched, and within a few years, Iridium Prime will be up in orbit as well. These new systems have something called a hosted payload, along with their main payload, which is the communication system. The payload is essentially what a satellite carries, and this hosted payload will allow scientists and other people to place their instruments and experiments aboard. So this summer, the Aerospace Engineering Group was challenged with creating a payload idea for the Iridium Prime system. Because the resources on the satellite are limited, we were given specifications for what we could put on the satellite. For example, our greatest obstacle was probably the mass and power requirements. Our mass requirement was 210 kilograms, which is about the size of a small piano, and our power requirement was 650 watts to about 1100, which is, for reference, small microwave uses about 800 watts. So since we, as a group, we decided that our payload has to be a lot smaller than the actual requirements because the payload is really expensive to put up into orbit. And this way we could split the cost with other people who will share the payload space with us. So our solution is a payload called COSMOS, which stands for Camera, Occultation Sensor, and Microorganism Observing System. The cameras are for observing the Earth and the satellite. The occultation system is for atmospheric characterization, and the microorganism observing system is for a biological experiment which involves observing the mutations that bacteria or cells go through with prolonged exposure to space environments.
As Claudia mentioned beforehand, our camera systems will be observing both the satellite and the Earth. On the observational side of the satellite, we will be using 2 camera systems here and here to observe the solar array. As spaceflight launches are becoming much more common, the danger of micrometeorites and space debris is becoming a lot more reality. As a result, the Iridium Prime system will host our Iridium Prime system payload will host an observational system to make sure that we can see any meteorites anywhere on the solar rays. And because the solar rays can rotate 360 degrees in this direction, you can see the entire solar array from our camera systems. The next grouping of cameras will be an observational camera at the end of the solar array right here, which will be able to view the entire satellite body, as well as the Earth. This camera can be used for media purposes for the Iridium company, advertising purposes for the Iridium company, or reselling purposes. It can also be used as a diagnostic camera for the entire satellite body. We are hoping that these two systems will actually be adopted by the Iridium system as diagnostic systems for their entire payload. The other 2 cameras are more scientific in aspect. We're using a spectral imager and a telephoto camera. The spectral imager is going to be working in the near infrared spectrum, and we'll be taking a global map of the Earth that's essential for agricultural and ecological research. Our telephoto camera will be taking high-resolution photos of the optical photos of the Earth that will allow us to either resell the photos for Iridium, to get a high-resolution images for scientific research and for other purposes.
So our second system will be the GPS radio occultation system, which will observe how radio signals refract as they pass through the atmosphere. An occultation occurs when an object, like the Earth, interferes with the radio signal between a receiver and a transmitter. In our case, we will be observing how radio signals refract as they pass through the atmosphere. In order to observe this, the Iridium satellite will need to receive a signal from one of the 31 satellites in the GPS constellation. When an Iridium satellite rises or sets over the horizon, a GPS satellite will send a signal out, which will pass through the atmosphere and refract. Then it will be received by the receiver on the Iridium satellite. From this, the receiver will be able to calculate how much the signal was refracted by using orbital geometry and so. Since Iridium is a constellation, only 12 satellites, or 2 in each orbital plane, need to be operating with the GPS RO system to maintain global coverage. From this, okay, 14,000 occultations will be taken per day. And, all right.
Okay, so the last part of our satellite payload is the microhabitat, which is actually a habitat which will host microorganisms. The reason we want to choose to include a microhabitat onto the satellite is because we want to analyze the effects of radiation and microgravity on life. For cosmic radiation, there is two things that greatly affect it. It comprises of solar and intergalactic rays, which have known to cause cataracts, cancer, and alterations in the DNA. And with this microhabitat, we are able to see those mutations through the microorganisms. In this picture right here, you can see the cosmic microwave background of the universe, and this shows us that radiation is riddled throughout and could greatly affect any movements towards sending humans to space. In terms of microgravity, it is known to cause bone loss. So there are several ways that we could test microgravity and radiation, and one of them could be on Earth. This way, you would blast radiation to microorganisms, but however, it is unlikely to get the same result because it is most likely that the microorganisms would not receive the same patterns in which cosmic rays affect in space as it likely would be on here. The other way is sending humans and animals to space. However, as you all know, it's extremely unethical, and it would be incredibly expensive because the environmental control and life support system for larger organisms is a lot higher compared to microorganisms.
Expanding on what Brianna said, we have devised a system for the maintenance and observation of a bacterial colony to be hosted on the Iridium Prime satellite. This will burn up on re-entry because you don't want a 3PDP like mutated bacteria contaminating the ecosystem. Okay. The system we have devised includes instruments for not only keeping the bacteria alive, but also monitoring its growth and mutation. The first of this is the thermal control system. Bacteria requires not a very specific temperature, but still requires a specific range of temperatures to be grown and to thrive in. And that's why, and if we want to get as much data out of it as possible, we're going to want it to actually grow, not just die immediately upon going into space. Next, we have an LC sensor system. This is used by this is used by companies in general to monitor bacterial growth in food and other products, and basically for quality assurance. And that's exactly what it'll do on here. It'll monitor the bacteria's growth, so we know whether the data we're gathering is even relevant. If the bacteria dies and we're still gathering data, that's a waste of everyone's time. Next, we have several independent DNA sequencers. These are important because as this bacteria mutates, we're going to want to be able to study exactly where it mutates, how it mutates, and that you can see in the DNA sequence. It'll change. And finally, we have a remote electron microscope. This is important because even though we're taking the DNA, we're monitoring the DNA sequence over the course of a lifetime of the experiment, you're going to want to be able to physically see how it mutates and what happens, and also view how it grows, like physically how it grows and what patterns it exhibits as it is subjected to microgravity and cosmic radiation.
The biological part of our project consists of the surveillance of the effects of radiation on our bacteria. For this, we will need a DNA sequencing system, and for that, we will need a minimum of 16 gigabytes for DNA sequencing tools and memory storage. We will also need a 2x2 terabyte hard disk for memory storage as well. We will need a DNA sequencing generator and compiler. There are two modes for DNA sequencing, which consists of exome sequencing and whole genome sequencing. And the digital code, the software provided must convert the digital code of 1s and 0s to A, C, T's, and D's. Then take this lowly text file and manually construct the model to represent. The mutation detections will be then sent to Earth, and the data will be used for further research. As for the imaging computing system, we will need 400 gigabytes compiled for image storage, and the cameras will detect anything that happens to the satellite, such as being hit by a meteor or anything like that, like the solar panel, and that will send a message to Iridium to be contacted right away whenever the satellite is detected to be harmed. So at the end of our satellite's life, it will deorbit and burn up.
So there are a few expected results of our payload. The first being that the Iridium company will be able to monitor their satellites throughout its life. This will help improve future satellite designs and also ensure that Iridium is notified in case its satellite has any damage. The augmentation system will be especially useful for scientists like climatologists and meteorologists because they'll provide a live view of the condition of the atmosphere at any given moment. This is key to understanding the effects of global warming on our atmosphere and helping us understand the different effects different things that happen in our atmosphere. Lastly, our microorganism experiment will help progress the future of human spaceflight by providing useful data about how cells and bacteria mutate while in space. As you can see, we were well under our specifications for our payload, which helped us create a very cost-efficient payload.
We would like to give a special thank you to Mr. Kenneth Robb, the Iridium Lead Platform System Engineer, Dr. Wallace T. Fowler, Graham Bryan, and all the team interns and staff. We're now open for questions. Any questions? Oh, yes.
Did you figure out which kind of bacteria you were playing with?
Okay, so we originally wanted to choose what kind of bacteria that we wanted. However, we are aerospace engineers, we're not really biologists, and so we decided to give it to give the decision to biologists so that way they could analyze what would be the most effective to see what organisms would best emulate what humans are like, because of course there's like prokaryotic and eukaryotic bacteria and stuff, and that wouldn't really help us if we chose for them.
Thank you.
Yes?
Do you know how the DNA sequencer would get the DNA from its bacteria?
Okay, so we did not exactly like show what the sequencer looks like. Can you go back? Yeah. Can you go back? Further back. Oh, so no, back. So up there where it says DNA sequencer, this image kind of reflects what it looks, what a sequencer looked like on the International Space Station called the MinION, not Minion, and it actually, yeah. So it's basically the size of the palm of your hand, and what it will do is if it comes into contact with an organism, it'll immediately sequence the DNA, and then it could be plugged into the to a computer of sorts, and so that way it will like sequence the DNA. Any other questions?
What was the most challenging part of the project?
Answering this question.
Probably the most difficult part of this project was going in and actually finding all the dimensions of all these different products that are not necessarily things that you find on the internet very often. A lot of these satellite computing systems, the DNA sequencers, the LC sensor, a lot of these things are very difficult to find any specifications for. So we were very grateful to the Iridium system. We were very grateful to the Iridium company, Dr. Kenneth Robb, and we really had to do a lot of research to find a lot of these specifications.
I think the most challenging part was probably thinking of something that no one's ever done before, because if you think about it, there's so many people with different satellite companies that already have satellites in space. So basically all our options seemed exhausted at the very beginning, but then we started brainstorming and I think we came up with a few original ideas. The microorganism one being an especially original idea.
Any other questions? Okay, well, thank you so much for watching our presentation.
So while our ICESaT team is getting ready, they can go ahead and come forward. I should tell you just a little bit about how the SEED opportunity became available. Several years ago, Dr. Tim Urban and I came up with a project idea to support satellite, Earth-observing satellite missions that are being managed or operated here at the UT Center for Space Research. And we invited area high school students to come in and work with our teams for 6 weeks. And they came every day. They were day students. So they were students in the greater Austin area. We did not provide housing or food or anything like that. So the students came and worked and then went home in the evening. So they didn't do any remote work. They did not do, they didn't have opportunities to really engage over the weekend or anything like that. When education and public outreach in science missions went away from NASA, we brainstormed and decided that we would propose to the Science Mission Directorate and ask and put in a proposal to make this a nationwide project. And it was funded last year, and we invited students from all over the United States to apply. This year, we had 617 applicants for the 43 positions. These are the 43 students that are here with us this week. I have to say, these are the cream of the crop. We could have selected any one of those 617 students. They were all outstanding. And the judging is probably the most difficult task for any of us, because we'd like to bring them all here, if that were possible. So we are lucky that we have several years of funding, and we're hoping that with new administration, that funding does not go away. As you all know, that is always something that we're looking at. So I believe that our ICESaT team is just about ready to start.
Okay, good afternoon, everyone. I wanted to thank you for coming to. Okay, sorry. I wanted to thank you for coming and watching our presentation. We are Team ICESaT.
My name is Rashid Aurora. I am a rising junior from Palo Alto, California.
Hello, my name is Benjamin Benjadol, and I'm a rising junior from Fort Worth, Texas.
Hi, my name is Max Bowman, and I'm a rising junior from Barrington, Illinois.
Hi, I'm Sally Winganeni, and I'm a rising junior from New Jersey.
Hi, I'm Annalise Goldman, and I'm a rising senior from Evanston, Illinois. My name is Rachel Penner, and I'm a rising senior from Albuquerque, New Mexico.
Okay, so as you can see, our satellite's name was ICESaT, and ICESaT is an acronym for Ice, Cloud, and Land Elevation Satellite. It was in orbit from 2003 to 2009, and it deorbited in 2010. It was part of NASA's Earth observing system, and its main scientific goal was to examine mass changes in ice sheets over time.
And aboard ICESaT, there was just one instrument, glass, with a geoscience laser altimeter system. And there were 3 lasers on glass for redundancy, and each of these lasers operated at 40 hertz, so that's 40 pulses per second, in 2 different wavelengths. There was a green wavelength and an infrared wavelength. And the way that glass worked was that it sent the laser pulses down to Earth and then measured the time it took for the laser pulse to return to the satellite, and that's how it determined elevation data.
Okay, so unfortunately, Laser 1 failed early on in the campaign. So to preserve Laser 2 and 3's life, the mission was split into 33-day campaigns. So as you can see up there, so as you can see up there, there's a continuous operation of Laser 1 and then an abrupt end due to the technical failure. And a short gap due to the investigation into the failure, then you have Laser 2's campaigns, then Laser 3's campaigns, and a short retry of Laser 2 at the end before the laser finally lost all of its power. Okay, so here are the 2 main parts of our presentation today. The first part is elevation models, and we did some cool things with our project this year. And one really cool thing that we did is that we were the first research team at CSR to read HDF5 files, which are the new file format that will be used in ICESaT 2 data.
And then on the waveform analysis side, we also use MATLAB to read HDF files and generate waveforms, and we also worked on correlating elevation data with the waveforms, as well as understanding a definition of roughness for a waveform, which we'll talk about in the waveform half of the presentation.
Alright, so the first region we're going to look at tonight is the White Sands region in New Mexico. This is a flat desert region that was once used as a U.S. military testing site, but in correspondence with ICESaT, it was used as a research site for the glass system. So what you can see here is the longitude versus elevation graph for ICESaT for White Sands. And this region is really flat and it's just next to what's probably a sand hill. So what's really important about White Sands there's a ton of things that are important. One is just that it plays a key role in mapping the total topography of the Earth or any other region. But this region in particular is important for 2 reasons. So one is because of the color of the sand. It's a very light gray, so it reflects a lot of light. And because of that, it was used to measure the accuracy of a reflectivity measure on glass. And the next feature is the flat area here you see actually extends for 20 kilometers. So this provided stability and constancy for the researchers to measure any changes in the ability of glass to measure the data accurately.
Hey everyone. So the second region that we looked at was the Salar de Uyuni region located in Bolivia. What it is basically just a bunch of salt flats, and it kind of plays a similar role to what the White Sands region does. So this large dip here is actually the actual salt flats, and as you can see from this graph as well, it's actually quite flat, which makes it perfect for calibrating the glass instrument. These rising and falling peaks over here are actually the adjacent mountain regions to the salt flats. So another key region that we looked at was the Jakobshavn Glacier, which is currently the fastest moving glacier in the world. It's located in Greenland. As you can see, the Jakobshavn Glacier is surrounded by rocky terrain on either side. So the Jakobshavn Glacier is actually this bunch of extraneous points right here. And on the other side right here, we can see the actual rocky terrain. The Jakobshavn Glacier is essentially a dip down from that rocky terrain. And what's interesting is that this rocky terrain does not reflect light as well. And because of this, the satellite needs to increase its laser power to get a strong signal, which is what the gain statistic measures. So we can see this on this graph right here, where on the part with the rocky terrain with the dark rocks, the gain is actually quite high because the satellite needs to increase its laser power to actually get interesting data.
So the next region we're going to talk about is Lake Vostok in Antarctica. This is a subglacial lake on top of which lies the Antarctic ice sheet.
and it serves as a Russian research station. So you can see two graphs here. They look at longitude versus elevation. The graph on the left shows that there are two tracks that are running over this region. The first one here that I'm tracing would actually hit the glass top, which is a flat area right here. And the second track missed it, but grabbed the area around it. And on the right, we have another graph of just Lake Basel. And you can see on the left that the scale is actually very small. It only increases by 1 meter. So all this is really showing just the general path of Lake Basel. And this region is important to research, especially in the future regarding ICESaT 2, to measure the impact of global warming on areas similar to this.
So another area that we explored was a summer camp located in Greenland. And the summer camp is basically just a research facility. Yeah, that's pretty much it. So basically, you might be looking at this graph and you're thinking that the summit of Greenland must be extremely mountainous and hilly. But in reality, if you look at the scale, because our scale is completely messed up, it's actually quite flat with a slight hill, obviously, but it's actually quite flat. So this red marker down the middle of the graph is actually the location of the actual research facility. And as you can see, it's next to, but not quite at the apex. As we look at the graph on the right, which maps the latitude versus the gain, we can see that at the top, right here, there was a lot of gain, which indicates that there was heavy cloud cover, so the laser power needed to be increased. And of course, we can see that this tapered off as we move east.
Alright, now we have Pine Island Glacier, which is important because it's responsible for about 25% of Antarctic ice loss. Alright, so looking at this graph, you see that the latitude scale, it actually covers 2 degrees. So this is a pretty big area. And what we see here in the middle in this red box is the actual Pine Island Glacier itself. And what we see on the sides are the ice sheets leading down into this glacial area. Now this is important because it shows us how ICESaT accomplished one of its main science goals, measuring the polar regions on Earth. It shows us that ice sheets are actually pretty rough. They have a lot of jagged edges. They're not completely flat and sort of shiny and silky like we kind of think of them usually.
Okay, so here we have quite a mouthful of an area. The greater Chicagoland area in the Midwest United States. Sorry. Okay. So as you can see here, you have Lake Michigan on the right, since Lake Michigan is to the east of Chicago. There's this flat area over here. Then you can see kind of a build-up area of urban sprawl here, and then just a slight increase in land elevation to the west. So as you can see, there's a marked difference between the gain levels of Lake Michigan and the land. That is because Lake Michigan has a darker surface than the land, which requires the satellite to amp up its energy in order to produce an acceptable signal.
Okay, so the next region we have are the Okavango Dunes in Botswana. And these are alien dunes that can be located north of the more notable Okavango Mountains. So both of these graphs here are longitude versus elevation. And as you can see, the basic topography of this area is just a row of hills, and the hills are each about 10 to 20 meters tall. And so you can see as longitude increases, the pattern just continues to increase to stay the same. And this is important because later when next let's talk about correlation, this area will have a really high correlation due to the competitiveness of the area. And another key feature you can see here is this scattered area right here that actually shows a lot of vegetation. And in contrast, the area where the hills are really dense over there, that shows an area where there's a lack of vegetation.
Alright, so now we're going to talk about Hawaii, and here we're talking about the big island of Hawaii. Okay, please. Alright, so here you see the big island is this large spike in the graph, but on either side is the ocean. So we're going across the island from, I think, west to east, yeah. So what's interesting is that here you see this blob, and you might think, what on earth is this blob? It's actually a cloud. So if we go to the next slide, we can look at this gain graph. This is latitude versus gain. And what we see up here at the top in this red box is a really high gain of 250. So that means that the satellite needed to amp up its energy a lot. And here we can see how gain can be used as an indication of cloud cover, and we can use this gain graph to also help us understand what we're seeing in the elevation data. Okay guys, now we're going to talk a little bit about the Grand Canyon, which produces very interesting graphs because you can definitely see a distinct correlation between the elevation data gathered by ICESaT and the physical topography of the land. So the Grand Canyon is actually up to 1,800 meters deep and varies greatly in width from about a kilometer, half a kilometer actually, to around 30 kilometers. So here, if you can see, there's this graph. It's a cross-section of the Grand Canyon, and it has big dip and all of this varied topography in the middle. It's because, like, in the picture, or if you've ever been to the Grand Canyon, there's lots of smaller canyon areas and, like, rifts and changes in the topography within the canyon itself. And the second graph is also the Grand Canyon, but you can see it's much, much narrower here. So this is obviously, the Grand Canyon is probably about a kilometer wide here at this graph, and has very sharp dips in the elevation. And the reason that there are two is because the canyon probably just like curved around over this specific area, because the river curved. So I think it's interesting to be able to see the correlation between the canyon itself and the wave, the elevation data. Another location that I looked at was the Bunda Cliffs in southern Australia. It's kind of a similar deal. You can see a correlation between the elevation data and the land itself. So here, if you notice, there's this graph. Here's the cliff, here's the water. And the cliffs are so steep that actually only 2 ICESaT footprints made it onto the base of the cliff itself. That's why there's only these 2 points here that are pointed out by the red arrows. And another interesting thing that you might notice is where the ocean is. You notice the elevation in meters actually says -20. Why is that? Well, actually it's because the Earth isn't a perfect sphere. Due to fluctuations in the gravity field, the sea level varies. So I was a little confused about the -20, so I looked up this graph. And if you look on around southern Australia, the sea level is this kind of like light blue color, which matches perfectly with the -20 meter data.
All right, so now we'll discuss some of the waveform analysis that we've done. So the first step was reading in the waveform data. So the waveform data we get comes from a data set called GL-Asia1, and that is the raw data from ICESaT. So let's just kind of touch on what exactly waveforms are. So essentially, when glass fires a laser, so it's got a 1064 nanometer, 532 nanometer laser, then bounces off of a reflective object on the ground. That reflected energy is going to be captured by a 1 meter diameter telescope or instrument. And this analog signal is converted to digital and beamed back to us on a ground station. And you end up getting something that looks like this. And on the y-axis, you have return energy in volts from the energy, and then you have time. So each waveform is measured over 544 nanoseconds. So this is what they look like. The value on the top is the standard deviation of the waveforms, which will come in handy later. And that just measures how kind of spread out the waveforms are on the x-axis. Okay, so we have 5 principal objectives when examining these waveforms. First, we wanted to compare the waveform data to topographical data. So we wanted to match some of the waveform data from the O1 data set with the elevation graphs we saw previously. Then we wanted to correlate single waveforms with topographical attributes like seismic and elevation. And using the correlations, determine a single footprint definition of roughness. So roughness has been defined with elevation, but it's never really been defined for a single waveform. So that would be interesting to come up with a definition that would reflect the surface topography as well as the waveform itself. Next, we wanted to test this definition and examine waveforms and their saturation in different surfaces, namely land and vegetation. Okay, so what is roughness of a waveform? There were 3 potential definitions that we decided to take a look at. The first one was width of a waveform. So from rising edge to falling edge, meaning so as soon as the waveform starts to rise to when it takes to fall. And then we also had standard deviation, or RMS about the mean, which is that value at the top you see here in the title of the graph, which just measures the variance of the waveform. And then also the number of peaks, which is number 1 through 6. So first, how do we correlate the waveform to the GLA H14 data set? So the GLA H14 data set contains elevation, saturation, gain, a lot of the properties that we use to generate those elevation graphs that you saw previously. So the GLA-H1 data set contains the waveform data. So how do we correlate these? How do we know exactly where a waveform came from and process attributes about like saturation? So in GLA-H1, each waveform has 2 parameters that we uniquely identify. One of those is an index, the unique index, and then one other one is a shot count. And actually, GLA-H14 also has a unique index and shot count. And we can figure out where those are equal, and that's exactly what we did here. So this is a spot in northern Canada, and at exactly this latitude and longitude, this waveform is fired by us. Okay. Additionally, over land, not vegetated, you'll get relatively high saturation, because generally the reflectivity of land tends to be higher than, say, water or vegetation. So the saturation of that waveform we just saw was somewhere around 1.12. And we'll compare that to vegetation. So this is Thompson-Nicole in British Columbia. And this was an area where we correlated some GLA-H1 data with some GLA-H14 data and examined the waveform from vegetation. So here's the results. You can see that the waveforms look a lot different than you can see. You can see that the width of the waveform, as well as the standard deviation, went way up, as well as the saturation over this is around 0.07, which is considerably lower. And the reason is if glass fires and laser pulse over vegetation, some of that energy is going to be reflected off the canopy, so you're going to get a peak of energy back. Some of it is going to get reflected off the ground, so there's another peak. And then some of this energy is going to be scattered to boost up through the vegetation, so you get like a little bit. And so because of that, you get lower saturation value, you get a much higher standard deviation value, as well as a much higher width value. Okay, so the first things we correlated, this is over 1 second ICESaT data, so 40 shots on the laser, as you can see on the x-axis, also time. And then you see the y-axis is normalized roughness and elevation. So this is standard deviation of the waveform, and then this is elevation of the waveform. So we didn't see too much of a correlation here, so instead of working with elevation, we decided to work with the slope of the surface and see if slope correlated with some of these waveform properties. And the way we calculated that was between the latitude and the longitude, we would calculate the distance and then the elevation change. So just like so standard deviation versus slope. You can see the Pearson correlation coefficient, the closer it is to 1, the more correlated the data is. In this case, it's about 0.12. And you can see kind of this common feature in both the graphs. So one of the problems with standard deviation as a definition was that if the waveform slightly askew, then it would throw off the definition. So then we tried correlating width versus slope. So if you're, say, firing glass over a sloped surface like this right here, some of the laser beams are going to get reflected, so the energy will get reflected with this higher part here, and it's going to come back sooner. Some is going to get reflected way down here and come back much later. So you're going to see a wider waveform. And just to reiterate, the width of the waveform is 1 inch. Okay. So here's width versus slope. You can see the Pearson correlation coefficient functions considerably higher than for standard deviation. And there's a lot more general key features that seem to Oh yes, and this is, we correlated width and standard deviation, which are 2 waveform properties, and they had a very high correlation of 0.92. And it was really interesting to see that two things that were very, very correlated produced very, very different results in terms of comparing them to the slope of the terrain. And so it would be really interesting to study why this is in the future and study this with more data. We'll study this over different surfaces with more variables to see what affects the waveforms, the waveform properties of the different surfaces.
So my main takeaway from this project was basically just how to conduct research, as in what kind of questions should we ask during the research process, and how can we use the data that we are given and analyzing it to best answer those questions. And in terms of my personal highlight of the trip, I think the robotics lab at the JSC in Houston was pretty cool.
My personal takeaway was I really learned a lot about the research process and how to analyze your data just to see what you can get out of it, and to be very curious about different about the data. And my highlight, of course, is phenomenal to work with Dr. Urban and others at Health Care Project, and I really, really liked the robotics lab at the Johnson Space Center as well as ISS Mission Control. I thought that was really, really exciting.
So the major thing I loved for this project was helping with a lot of people working closely with programming and MATLAB, testing out data into graphs, and just recognizing key features and learning how to deal with them, like Emily mentioned before, like the class and stuff. And probably my most favorite part of this internship was seeing the buoyancy lab. I just thought it was really cool to see how intricately both scientists and team has to work together before going out into space.
All right. Honestly, for me, working with MATLAB was incredibly frustrating. I'm not going to lie about that. I am very new to coding, but this experience has definitely made me want to learn more. I also gained some exposure to cryospheric sciences, and I'm now definitely considering that as a possible career option. And my favorite part, of course, was JSC, but I loved the mega lab there where they were analyzing Mars data. And also I loved working with our team, they were great, so yeah. You're welcome.
Okay, so personally, most of my academic background is in geography, and also in my rocketry and engineering classes, we use good old pencil and paper to do our calculations. So MATLAB was also a new concept to me. I really enjoyed learning how to use MATLAB because it's a really powerful engineering tool, and I would love to learn more about it in the future. My favorite part of the SEAS experience was probably Johnson Space Center, especially going to see the moon rocks, because there are very few other things that you can ever see in this life that will ever compare to seeing moon rocks. Because not everyone gets to see that, and we were very fortunate to have that opportunity.
For me, this project was definitely very challenging, but I don't think that that should be a bad thing. I learned so many new things when I was faced with this challenge of struggling with MATLAB and trying to learn all these new things all at once. I think that it really has helped build my character and learn how to really face these challenges in a scientific environment. For me, of course, JSC was amazing, but I think the real highlight of this trip was internship, and a trip from here, was being able to work with all of these amazing people, all of these very, very intelligent and talented other interns from all across the country, as well as, of course, Dr. Urban, without whom this would have been literally impossible. So there we go. Okay, so as Rachel was saying, thank you, Dr. Urban. We could not have done this without you. And also thank you, Mr. Dennis Felixson, for helping us with our MATLAB code. And thank you to Ms. Baggio and all of the other SEAS staff for making this possible for us. So we hope that you've learned about how ICESaT works and how it was used, honestly, not only to study polar regions, but also the rest of the Earth. So on that note, do you have any questions? Yes.
So you guys mentioned that sometimes they had to use a little bit more gain to get some more information. Do you know how much of that energy was absorbed? And I know you mentioned something about the different like vegetation was reflecting difference in water and like rocky areas. And so did y'all ever look at how much of the energy was absorbed with the different terrain?
So we measured the saturation, actually not the gain, but the different surfaces, so the saturation is essentially how much energy are we getting back, and we measure that over land and vegetation, and vegetation has a lower saturation value because it has a much lower reflectivity. But no, we did not measure gain over different surfaces that we did do gain, which we saw in the emission graph.
And actually, gain can be thrown off very easily by clouds, so it's very hard to account for that, especially when looking at different topographical surfaces. Any other questions? Yes, Brianna.
So what led y'all to analyze those certain locations?
We just wanted to, it varied. A lot of the reasons we chose a lot of glacial regions because that was ICESaT's primary mission, to look at ice sheet mass loss. But we also chose different regions because we thought they would generate very interesting elevation graphs.
A lot of the major reports we looked at were, like, we have a couple of criteria over ice, vegetation, flat areas like where it's and yeah.
We also chose, so a lot of Uni, you saw that, and one of the things we started, we chose specifically because they were used extensively as verification sites for ICESaT, and so we knew what to kind of inspect over those, so we decided to generate graphs over that to make sure they're checked out.
Great. Please join me in thanking the ICESaT team. Tom, if you'll let me know.
Hi, to the Lunar Exploration Group. My name is Shara Allen. I'm Party Adam.
I'm Sebastian Perez Lopez, and unfortunately one of our team members had to go to another commitment, but you guys will be lucky enough to see his designs later. His name is Ian Sloan.
And I'm Maya Tapp. So we decided to focus on the lunar South Pole as our area of interest for a couple of different reasons. The number one reason is because the sunlight hits the surface of the moon at a very oblique angle in this region. It's nearly perpendicular, which causes it to barely graze the surface, which causes the peaks of eternal light at the topographical highs, such as mountains and other high elevations, and causes topographical lows to be nearly in darkness, extremely cold, reaching temperatures as low as 25. So why is this even relevant? Well, cold traps, the areas of topographical lows, which are basically craters, have been known to harbor water ice, which is a valuable space resource that a lot of companies and space agencies are going to be vying for in the future, as transporting water from Earth to space is very expensive and requires a lot of infrastructure. So compared to that, it would be easier to have a resource for water already in space. So you might be asking, how do we even know there's water ice? Does it even exist? So there's been a lot of evidence for that. So first thing that they did was that they had neutron spectrometry performed, which basically detected excess hydrogen in this region of the moon. We weren't sure at first if that was actually water, so we had to do 2 more experiments with radar reflections and LCROSS. So radar reflections basically showed that there was water ice on the moon because the reflection that came back to the data showed that it was conducive to H2O. And LCROSS was a satellite which impacted on a crater, and when it released a plume of dust and other materials, it detected water vapor in it as well. So there is ice on the moon, and there is water on the moon. So companies and space agencies are going to be going there to mine for it with their rovers. And these rovers are going to need power, heat, and water storage facilities, which is something that our company, the Lunar Ticks, is going to be providing with. It was very interesting. So Lunar Ticks is basically going to be the #1 space company, we hope, because we're going to be providing this energy and heat and water storage for the rovers, assuming that they can't do their own energy infrastructure, as it would be costly to them and not economic. So our basic concept of operations includes our users, our operators, and our developers. So So our users, as I said before, are going to be the space agencies and private companies that want to mine for ice on the moon. We're going to be providing them with heat, water storage, and energy for their rovers. We're going to actually develop our utility stations in Thermowadi, which is something we'll explain later, by using robots to assemble and build on the moon. And our developers are going to be element designers, using CAD software, which is something our team member Ian, who's not here, actually does. So this is our decision tree, and it shows the thought process that our company went through to figure out the best lunar utility station. So first we're going to talk about power. We had to figure out how much power was needed for each rover, so we based the rovers off of a Ford Ranger 2011 pickup truck, and we found that the minimum power needed would be 5,000 watts, and power needed when there was ice deposits in the rovers would be 9,000 watts. And we figured that out by calculating the maximum amount of ice deposits the rover is able to hold. So first we tried to use laser beaming to power the rovers, but our technology is not up to par. So currently it only beams up to 1 kilometer, which is not far enough for us. So then we tried solar panels, which currently the average is 22 to 23 efficiency, and the best efficiency we found was 50%, which is still not good enough. And we had to consider lunar dust, which would cover the panels over time, affecting them, and the laws of thermodynamics. So as heat rose, the output would decrease. Then we try to use RTGs and MMRTGs, which use the decay of plutonium, but it only provides 110 watts of power, and they're $36 million each, and we would need at least 45 just to power 1 rover, so that would be very cost effective. So we ultimately went with a fission-based nuclear reactor, which uses uranium, which is much more abundant in the crust, and it provides 40 kilowatts of power. So this is Ian's calculations, and he unfortunately had to leave. But what we had to do was we had to find the specifications for the lithium-ion batteries, and we found that the specific energy is 263 watts-hour per kilogram. The energy density is 693 watts-hour per liter, and the cost is 2.5 watt-hour per US dollar. And what we figured out with that is if a rover needs to travel a max of 80 kilometers and 32-hour drilling time, 224 kilowatt-hour batteries are required, and you would need 323 liters of space for the battery. And it will cost around $89,600. So the charging time. So the nuclear reactor provides 40 kilowatts of power, and we'll have 3 charging stations, so each battery will hold 8 kilowatts of charging time, taking around 32 hours to charge. And this is Ian's power utility station he designed on a CAD. Okay, so now I'm going to talk about the Thermowadi. But before I actually speak of that, I want to tell you a little bit about the lunar environment. So firstly, the lunar regolith, which is the fine, dusty, rocky dust that coats the lunar surface, it has a high thermal contact resistance, meaning that the temperature of the regolith won't change too easily. So in other words, it has a pretty high specific heat. Secondly, it has a low thermal reflectivity, which means that any heat that is put into the regolith won't diffuse out to colder areas at a high quantity. Unlike the Earth, the Moon lacks an atmosphere, so any heat that does go onto the Moon will be radiated out and lost to space, leading to extreme temperature. Temperatures can be as low as negative 200 degrees Celsius and rise up to negative 50 degrees Celsius in the poles. And on any non-polar area, it can go as low as negative 150 degrees Celsius and rise up to 100 degrees Celsius. And the picture to your right shows the temperature swing on the south pole of the Moon. The redder is the hotter, the bluer and purple is the colder. So the right side of the image represents daytime, and the left side of the image represents daytime, and the right represents nighttime. And the red spots, as you can see up there, but the red spots represent 300 degrees Kelvin, and during nighttime, in the little purple areas, for instance, that the temperature can be as low as 25 degrees Kelvin. Okay, so Thermowadi, what is it? Thermowadi is a heat-insulating umbrella that will provide protection and warmth to electronic devices or rovers during nighttime and temperature falls. Why should you consider it?
Well, soon in the near future, there's going to be a lot of protecting rivers, extracting and searching for resources on the moon. And we have to keep in mind that there are 14 days at night, and temperatures can be as low as negative 10 degrees Celsius. Unfortunately, electronic devices or rivers in our case cease to work at negative 55 degrees Celsius. So, with our warming safe havens or thermal wire placed down close to the moon, the productivity and the work time of these rivers will be maximized. So here are some materials to consider when you're building a thermal body. You'd want to use a lighter metal so that the payload on the Earth won't be too heavy. You'd also would not only want to consider a solar reflector or mirror, but also a tracker as well, since the sun hits the poles of an elevated angle. And lastly, you need a thermal pad, and we will produce this by modifying the lunar regolith since it's not a good candidate for a thermal mass. And we will do this by using concentrated microwaves to melt it into a solid mass. So how does it work?
Looks like this.
So this represents the thermal body during the daytime, and the umbrella. Okay, so this is it during nighttime. It will raise up and goes up, and the sunlight will hit it and reflect down to the thermal mass. And as that is happening, the thermal mass will store any of the thermal energy that is placed on it. So during the nighttime, the heat umbrella will come down, and the thermal masses will radiate into the heat that it has still emitted and warm it over, and the umbrella will just insulate any of the heat so that it doesn't radiate out into space. So earlier I mentioned that we cannot use regular regolith to add the thermal masses, and this is why. So down here is a chart, and it compares the regolith and the basalt rock. And the basalt rock actually mimics the thermal mass that we on the moon. So as I mentioned earlier, the thermal diffusivity of the lunar regolith is a little low, and the specific heat or the thermal contact resistance is pretty high. And as you can see with the basalt rock, the thermal diffusivity is higher, which means that more heat will diffuse out of it, and the specific heat is also lower, which means that it will heat up faster. I'd like to also mention that it has a higher thermal conductivity, which means that more heat will flow out of it at a higher rate than the native regolith. So overall, the basalt or the modified lunar regolith is a better candidate because the heat will diffuse out of it at a higher quantity and rate, and it heats up much more quickly than regolith does. Okay, so we decided to turn our thermal body into a rest station, and we decided that each station will have 6 parking spaces, and each parking space will have access to 2 storage compartments. So when it came to dimensions, I had to keep in mind that I didn't want the thermal body to be too big because it had to fit in certain locations that Sebastian gave me, and I didn't want to make it too small because we wanted to have as many parking spaces within a station, but we also wanted the parking spaces big enough to go for it. So I decided that each station would be 22 meters squared, the parking spaces would be 6 meters squared, the storage compartments would be 2 meters cubed, the umbrella will also be 22 meters squared, and the height of the thermal model would be 2 meters. And this is a depiction of what our thermal body station would look like. The squares that lay on the lunar surface, those represent the thermal masses, where the rovers will drive onto and warm up. The top thing that looks like an umbrella, that is the insulating umbrella, of course. And the squares that are on the rectangular prism that is in the center, those represent the storage compartments that the rovers will actually use. And this was made on CAD by me.
Alright, so none of this really matters if we can't find locations that are going to optimize the efficiency of both the thermal body site and the energy site. But before I begin on how I chose these locations, I want to talk a little bit about the Lunar Reconnaissance Orbiter quick map that I used. Basically, the Lunar Reconnaissance Orbiter has this camera that mapped the entire surface of the moon, and I was able to overlay it with maps of polar illumination, solar saturation, rock abundance, and things like that. And you're going to see a lot of pictures from this quick map later on. So what determines the location of a utility site? I looked at 2 criteria, those being the nearness to a predicted resource site, whether it be water, coal, volatiles, or any resource that's going to be built in the future. If the energy site's too far away, it's not going to be useful.
I also had to take into account the topography of the nearby area. If we put the energy site at the top of the mountain or at the bottom of the crater, or on a really, really steep slope, the rovers won't be able to get there easily, and so it's not going to be much use to us either. So these two maps here I used to determine the nearness to a particular resource site. The map on the left shows the albedo ratio of the lunar surface, and albedo pretty much just measures the reflectivity of the sun. Anything you see in blue mimics the albedo levels of water ice, and then I just found 3 locations that I thought had a high abundance of that. The map on the right shows the sublimation rates of the lunar regolith, and basically anything that's orange or red shows possible resources at the surface. And this would really be the ideal environment for these rovers to prospect because it would be much easier and much more efficient than having to take them into the future. So I just overlaid these 2 maps, and I found that there were 3 areas which I named location A, B, and C that predicted nearness to a resource based off of both albedo and sublimation rates. And it just so happens that when you look at these 3 areas in the quick map, they do have elevations and topography that are conducive to an effective energy site. So I made these my energy sites. And then what determines the location of a thermal wadi? For thermal wadi, I had to look at sunlight and surface temperature. Sunlight's pretty obvious because without sunlight, the umbrella won't be able to do its job. And to look at sunlight, I actually just have to look at the elevation. So as Kachi said on the first slide, because of the angle that the sun hits the lunar south pole, the only way to get constant to somewhat constant sunlight is if you're at a really high elevation. These are called peaks of eternal light. The map on the left shows an elevation of the lunar south pole. Anything that's yellow, orange, or red are elevations of 4 kilometers or higher. And once again, I just found 4 areas that I thought were high enough elevation. Then I also have to look at the average annual surface temperature, because even if we got all the sunlight in the world, if it was too cold average throughout the year, the thermal wadi wouldn't be affected. So in the map on the right shows the average annual surface temperature of the lunar south pole, and anything you see in red and orange are surface temperatures of 175 degrees Kelvin from the equator. And I just overlaid these 2, and once again I found 2 sites, which I named thermal wadi site A and thermal wadi site B. Thermal wadi site A actually ended up being on Malpert Peak, which is the highest peak on the lunar south pole. It's one of these peaks of eternal light. The thing about Malpert Peak is that it's humongous. It's actually 123 kilometers squared, which is way more than what we need. And if we just zoom in quick on the quick map. But I found that at the southeast edge of Malpert Peak, on the little purple cove at the bottom right of that picture, it's pretty flat and it still gets a lot of sunlight and it's still pretty hot throughout the year. So that's why I decided to put thermal wadi A. And later you'll notice that thermal wadi A is actually right next to energy site A, which would be perfect. Thermal wadi site B, however, was not perfect. There were a lot of things that made it impractical. The first one just being that every single energy location was closer to thermal wadi site A, so it wouldn't make much sense for a rover to drive all the way out to thermal wadi site B. If you look at the numbers in that graph, the distance to thermal wadi site B could be as big as 200 kilometers depending on where the rover was. The travel time could be up to 2 days, and the power that the rover needs to spend to get there would just not be feasible with the lithium-ion batteries we plan on using. So I decided to scratch thermal wadi site B, which means the final map that looks like this. It has 3 energy sites located in kind of a triangle. Both thermal wadi site A on the northern tip of that, right next to energy site A. And there are a few glaring holes here. The 2 things that I want to look at are putting an energy site right in the middle, because that would cut the max travel times for all these rovers almost in half, which would save power, time, and energy. And also, that crater right there, there's a crater there called Shackleton, and it actually gets a lot of sunlight on its rim. The thing about Shackleton, however, is that it's too cold over the entire year, but I'm confident that as technology improves, we will be able to put a thermal wadi on the rim of this crater that's going to be effective. And then just for some perspective, this shows the entirety of the lunar south pole on the quick map, and that orange box is the area that's zoomed in on the left. So there's still a lot of space that we have to put energy sites in, figure out locations for, and this is really just a small piece of a much larger part.
So once we actually get all our utility stations, thermal wadi on the moon, we're going to need a communication system so that we can provide services to our rovers, for our customers. So the first thing we had to consider was the type of satellite that we were going to use. So there's 2 main types of satellites that will be used for communications in this situation, CubeSats and smallsats. So CubeSats are basically nanosatellites that are standardized in size and form with a volume of about 10 centimeters cubed, versus smallsats, which are more customizable. They have a larger range of sizes, ranging from 0.1 kilograms to 180 kilograms. So we chose smallsats because we actually based our communication satellite model off of a mission called LADI, which was a successful laser communication demonstration. It's currently not in orbit, but it was successful for the job that it's designed to do. So we chose small satellites. The next thing we had to consider was how exactly we were going to put the satellites in orbit. So we decided we were going to go with 3 satellites, each 120 degrees apart with an inclination of 51 degrees, and an elliptical orbit with an eccentricity of about 0.6. These figures, in fact, were all provided by Tade Eli, the Senior Director of Navigation, Control, and Guidance at JPL. We also decided we were going to go with a 0.5 watt laser for transmission, once again also inspired by the successful LADI mission. The last thing we had to consider, as I mentioned before, was the type of laser we're going to use. I did say we were going to use laser, but that wasn't always the case. We first thought we were going to use microwaves or radio waves, but in the end we decided that they would simply be too broad and scattered for the type of communication we want, since we want like a narrow range for far distances. So this is our satellite, PETI. It stands for Polar Encircling Transmission Transferring Infrastructure, and it was designed by Ian on CAD. You can see there's solar arrays on either side. To power PETI, there are rocket engines at the top, and there's a laser transmitter and receiver on that side. So this is basically the way our communication system is going to work. We have the rovers that our customers have adhered to our specifications. We're going to provide them with the laser transmitter and receiver modules. We're going to have receiving stations. An example would be in White Sands, New Mexico, where the LADI receiving stations were. You would have to have multiple stations around the globe because we're not always going to be in the same line of sight. So that's something that we would have to consider as well. And as you can see, we have our satellites in.
Right, so another thing we have to think about were our future initiatives. As a business, we always have to be looking ahead to try to stay ahead of the game. And for us, that meant trying to take advantage of the processes and resources that we could find on the moon to provide energy. This would cut the cost of transporting things from Earth constantly, and it would be really useful to us. And there are actually a lot of resources on the moon that we can use to provide energy in the future. Some of them being silicon, which we could use in the creation of solar arrays. There's also a mineral called ilmenite, which is rich in oxygen and hydrogen. And there's a little thing called helium-3. So because the moon doesn't have an atmosphere, it actually gets bombarded by solar arrays. And there are large quantities of helium-3 on the moon, which could be used for nuclear fusion. So as a lot of you know, we don't have the technology for nuclear fusion yet, but once we do, that could be a really interesting energy source. And finally, there's thorium, which can be used in nuclear fission. This is particularly important to us because we are using nuclear fission reactors, so that's something we're looking into. And there are also lunar lava tubes, which are pretty much just empty tunnels and sort of openings under the lunar crust from lava tubes that have already flowed out. And these can provide sort of a natural safe haven for our energy sites and thermal body to protect them from solar rays and lunar dust and anything else that might harm them. And then we'd just like to thank Dr. John Lunar for helping us and giving us this idea, and Tom Ramirez for being with us every day and dealing with it. Yes.
I think we have time for one question. Yes.
How did you choose the South Pole over the North Pole?
So that's an interesting question. That's sort of, there's no answer to that. We talked to Lunar with that a lot, and it's just, for some reason, every single country decided that the South Pole is the place to go. There are water deposits that have been detected on the North Pole, but the South Pole is just the area that's chosen.
Great. Thank you. So the moon team expressed their regret that their teammate could not join them this afternoon, but he was selected for an international space settlement design program and is on the way to Kennedy Space Center right now. So we got to hear their presentation twice today, and I appreciate their filling in for their teammates this afternoon. So our next presentation is by the Emergency Preparedness team.
analyzing the American River flood 2017. We're going to go ahead and introduce ourselves. I'm Janine Fleming.
I'm Jennifer Terry.
I'm Richard Holmgren.
I'm Valerie Chen.
I'm Sam Mosby.
And I'm Sarah Camino. Okay, so a little bit about the Merrimack River flood. So the Merrimack River is located in the state of Missouri. And so the flood took place between April 29th and May 9th of 2017. Okay, so this area receives a lot of rainfall, and to top it all off, like to make matters worse, this area has no aquifers currently. So basically what could have, like permeable rock could have contained some of the groundwater, but there isn't any form of flood control there. And also this area also has lots of steep terrain, and so it increased sediment runoff. In the 1900s, they were about to make some type of flood control and implement a dam, but environmentalists just wanted the free-flowing river. So. And this led to the result of a flood that killed 5 people. So on the left, you can see the Merrimack River watershed, and on the right, it's the gauge height of a city that was affected by the flood, Eureka, Missouri. And so you can tell that on April 27th, which was the day prior before the flood, the gauge height was only at 5 feet, but then it increased steadily, and then it reached a peak at May 3rd, when the gauge height reached 45 feet.
Now, as my colleague mentioned, Eureka, Missouri, saw flooding and took damage from the flood. One of the buildings damaged was the high school, as you can see here in this picture. The water is surrounding the high school in this picture, and in this picture is the high school's recreational field. As you can see, none of it is left. It is all submerged. As you can see in these pictures, just truly puts them in perspective, how the field was just completely submerged. Water was overflowing the campus. And here is our satellite images of the Missouri River system. As you can see, the Mississippi River also saw flooding, along with the Missouri River and the Merrimack River, which is what we are studying here.
Alright, so there are many ways that we can analyze the flood, and one of them is using satellite images. So this image was collected by the Landsat 7 satellite, and you can see the Mississippi River here, the Missouri River, and the Merrimack River going down the center. Now, another way we can analyze flood is using aerial data. And so in order to do that, let's look at Valley Park, a small town on the river, in order to get a close look. Alright, so this is one of the highway intersections in Valley Park. And as you can see, this area is completely flooded over. I'd like to point out that actually the river is not in this image. It's to the right of the image, quite a ways away. So the river water reached such a great height that it actually flooded an area so far away. Right, so here is one of the images of the flooded highway. You can see the signs are almost covered over. That's how high the water was. Right, here is the area from another view. Let's take a look now at the railroad bridge in the red box at the upper right-hand corner. Right, so this is the bridge on May 2nd. So this is during the peak of the flood. And as you can see, the railroad bridge, which normally clears the river, the bottom is flooded completely. Also, the trees should be on the banks of the river, but you can't even see their trunks because the water is so high. Right, now an interesting thing is that the ESA, or the European Space Agency, actually made a flood map of the river flood. So the light blue areas are the areas where it's flooded. But this red box here is Valley Park, and as you can see, it's not labeled as flooded. And so when we looked closer, we realized that it was actually made from data taken on April 30th. And so this really stresses the importance of using all different kinds of data to look at the same flood in order to get one picture.
Now I'm going to be talking more about remote sensing. So basically remote sensing is a device of satellites that is not in direct contact with the surface, and the satellite has sensors that collect scattered or reflected light from different wavelengths along the electromagnetic spectrum. So we have 3 features of remote sensing. The first one is a platform, and so basically the altitude of the satellite or device, and that determines how much the sensor will detect. And we also have satellites, especially orbits. So we have geostationary orbits, which basically the satellite goes around the Earth at the same place at the same time, and so that helps with like communication and weather forecasts. And we also have the low Earth orbit, which helps with global coverage and also scientific measurements. So we also have passive and active sensors. And so passive sensors is basically where you have the sun's light reflecting down off the surface and then coming back up to the sensor, whereas active sensors are where they have their own source of energy. So what is SAR? SAR is synthetic aperture radar. It's basically an airborne active side-looking radar system, which simulates a large antenna. And so basically, by it being an active sensor, it allows it to get images during the day and at night. And by it being side-looking, it allows you to figure out the location of the surface. And then by simulating a large antenna, it allows it to have a higher resolution. Okay, so now intensity of the light that comes back to the sensor, it varies depending on various parameters. And so the first one is wavelength. So the longer the wavelength, the more penetration it will get. So like for example, SAR, it's measured by microwaves. So basically, it allows it to penetrate deeper into the canopy and forests and soil. And then we have polarization, which is basically the direction of wavelengths on a plane. And so you can have horizontal wavelengths or vertical wavelengths. And then the incidence angle also allows you to show the influence. It influences the image brightness. And then we also have surface parameters. So we have the amount of objects in an area, size and orientation, wavelength, and dielectric constant. And the dielectric constant basically measures the conductivity and reflectivity. And so you can figure out if the surface is dry or moist. And the more moist it is, that means that there's more backscatter coming back to the sensor. And then we also have smooth and rough surfaces. And so right here, that's basically a smooth surface, and it's showing that the reflected light is going away from the sensor. So that means that if you were to see the image, it would appear to be darker. And then we also have what it would look like with a rough surface, and the scattered light is coming back more. So that means that it would be lighter in the image and brighter. And then there's also distortion and shading as well.
So I'm going to talk about Sentinel-1. And so Sentinel-1 is a constellation of 2 satellites, Sentinel-1A and Sentinel-1B, both of which are part of the Preparedness program launched by the ESA, European Space Agency. And their goals were to collect data on the environment, climate change, and civil security. Now, both of the satellites, Sentinel-1A and Sentinel-1B, they both send and receive microwaves, and they have C-band on board. Now, Sentinel-1A was launched in 2014, while Sentinel-1B was launched in 2016. And they're able to image the entire planet within 6 days. So in order to analyze the data we got, the SAR data that we got from Sentinel-1 satellites, we use a platform called SNAP. And now SNAP is developed by the European Space Agency. It's freely available and open source, and it contains toolboxes and methods that we can use to perform image processing on our data, and on SAR and also data. Now I'm going to go over the image processing steps necessary to be able to analyze SAR data. So first you have to calibrate your images. Now calibration actually creates an image where the value of each pixel becomes directly related to the amount of backscatter coming from the area, coming from that pixel. And now your second step is to be able to convert the strength of your backscatter and power scale into a logarithmic scale, which is measured in decimals. And next you have to perform an image analysis. Now this can be binarizing the data, performing image classification, segmentation, whatever you need to perform your process. So this is an example of Galveston Bay, Texas, and this is just an original image of Galveston Bay taken by the Sentinel-1A satellite. And if you were to look, this is what the satellite image looks like after you perform radiometric calibration. Now this kind of calibration actually accounts for radiometric distortions such as speckle, which is your wave interference, non-uniform antenna patterns, differences in gain, saturation. Radiometric calibration helps calibrate and account for those kinds of radiometric distortions. And you can see it looks a little bit clearer than the previous image, but speckle filtering helps greatly reduce the amount of speckle and graininess in the actual image. Now, what speckle filter does is it actually takes the standard deviation of all the pixels in a square window, and it averages the values of the pixels that are within that standard deviation calculated, and that value becomes the new value for the central pixel in the square window. And it does this for every single pixel within your whole image. And you can see that the image becomes a lot clearer and much more easy, and it becomes a lot easier to interpret. Now, this is an example of the multi-look method, which can also be used to reduce your speckle. Now, multi-look actually takes a look at your image at multiple angles and multiple looks, and it averages the pixel values in all those looks, and it creates a new image, which consists of those average pixel values for your for a new image with reduced speckle. Now, in this case right here of the Merrimack flood, you can see that the multi-look actually outperforms the speckle filter because it actually covers some areas which are missed by the speckle filter. So in some cases, multi-look might be better than speckle filter, or vice versa, and in some cases, there might not be any distinction between the two. So this is an example of what the image looks like after terrain correction. Now, terrain correction is actually a form of, it's actually geometric calibration, and it accounts for deformations and distortions in the terrain using a digital elevation model, a DEM, which is created by the data generated by interferometric SAR data, which is also collected by Central 1A and Central 1B. Together they can create pairs for SAR data.
Okay, so using the steps that Rishu just described, and then we will use Sentinel 1A data, and then we're able to make our own maps of before the flood, during the flood, and after the flood. So before the flood on April 22nd, you can like barely see anything after like mapping it out and stuff. And then on May 4th, which was during the flood, you can clearly tell where like the flood occurred and then the extent of the flood and how devastating it was.
Okay, so I'm going to be talking about one of the other satellites that we got back from Landsat 7. It was a joint collaboration between NASA, NOAA, and USGS. It is part of the world's longest continually acquired collection of space-based remote sensing data. Its applications include agriculture, forestry, geology, and for us, emergency disaster planning. And the main instrument on Landsat 7 is the Enhanced Thematic Map, or the Enhanced Thematic Map Plus. It's a multi-spectral spanning radio meter that has 8 bands ranging from visible light to shortwave infrared. Another software that we used was QGIS. QGIS stands for Quantum Geographic Information System. Pretty much QGIS is just used for analyzing, editing spatial data from satellites, and you can create geographical maps that are easy to interpret and easy to use. There are a lot of features within QGIS that you can use, but for this project specifically, we used and analyzed and edited raster and vector layers to compose our map.
So now I'm going to talk about how these images are created, for example on Landsat 7. So basically this is a raster, and it's basically like a grid. And so basically all the squares are pixels and dimensions of like the spatial resolution. And so the lower values represent greater reflected light back to the sensor, so that means that it would appear darker. And then with higher values, then the pixels will look brighter. And then, so we turn that black and white image into a colored image by assigning colors to it, and then we can understand the image better and interpret it better.
So these are relations to what Jennifer just said. This is also in relation to spectral signatures. So spectral signatures show how surfaces reflect different wavelengths at different strengths. So I'll give you an example. Green vegetation or like leaves. So leaves usually reflect green visible light, near infrared, and mid infrared light. And just shown on this graph right here, where the peaks are right there is where it has the highest reflectance. So for example, if you're looking at a satellite image that was a band with, let's say, near infrared light, the green vegetation would be represented by the places that have like the brightest values on that satellite image. So this is one of the images that we edited in QGIS. This is before the flood on April 23rd, 2017. I'm going to go over what all of that stuff means on the image. So the yellow outline around here is the watershed around the Maryland River. The green represents vegetation, the red represents rock and sediment, and then the blue represents water. So one of the coolest things about QGIS is that you have the option to build a virtual raster. This pretty much means you can combine multiple bands of a satellite to create one image. So in this image right here, we combine green visible light, near infrared, and short infrared. And it depends on like what you want to see in like that satellite image, because either band can highlight different things. For instance, we wanted to highlight something that would highlight where the water or flooding areas were around the Maryland River. We use those bands as propagation events. So this is an after image of the flood on May 9th, 2017. So you can see along the Missouri River and the Mississippi River and the Maryland River, there's a lot more water and sediment piled up there. If you remember from the aerial photography that Sam and Valerie were showing you earlier, how that water is brown, the sediment represents like that flooding water, since there's a lot of erosion when the flooding happens. We also use Sentinel-1 data, as Michelle and Jennifer were talking about earlier. The way we can edit that is a little bit different, since Sentinel-1 wants its images based on the backscatter. So we use this method called thresholding that pretty much classifies the images into two separate things. So on this image right here, the light parts represent the water, and the dark parts represent land. And then this is during the flood on May 3rd, 2017. And then this is after the flood, so where a lot of there's still flooded areas present, but a lot of the flooding has receded since when the event happened.
So another pretty cool thing we can do using QGIS and SAR data is make this kind of image. What we did is we took data from 2 different days, May 3rd and May 22nd, so right during the flood and after the flood, and we put 3 of their bands together. So the blue areas that you see here are actually the differences in the 2 images. So it really shows the extent of the flooded area.
So I'm going to talk about why you should care and why our work matters. So our work can be used in the future to better prepare first responders and emergency teams in future flood events in areas that are similar, in areas with similar structure and landscapes to the Missouri-Illinois area. Our data can be used for those first responders to predict which areas will be flooded, and that way they can prioritize which areas they need to go to save the most people. And this can help prepare and warn inhabitants in certain areas ahead of time, because if there's certain flood events happening and they're in areas that are likely to be flooded, then they can know beforehand that they need to evacuate. So I'm going to talk about future work and improvements. So one of the ways we can improve our work is to increase accuracy of our classification by using convolutional neural nets, which are commonly used in image-based deep learning. And we can also analyze data from other independent sensors to help verify findings and verify conclusions. And we can also connect SAR image processing to INSAR coherence, which is the phase noise of the backscatter coming back. So we can connect SAR image processing with INSAR coherence to for a better flood mapping of before, after INSAR image pairs, and that can help us more accurately map flooding. And we can also look at better data compression algorithms, which can be used to download large amount of data in short amount of time, which would be really useful. And if we had more time, we could have tested more digital elevation models and different kinds of spectral filters to see which ones would work the best, and we can optimize our image processing to those filters that work the best.
A big thank you to everyone who helped us with our work, especially our wonderful Miss Teresa Howard. Any questions?
Is there any way to detect loose soil from your data also, like to predict how much erosion is going to happen during the flood?
Not necessarily like the satellite images that we use. that I can look it up and get back to you on that.
I also believe you can use other kinds of sensors as soil and moisture data, such as using the soil and moisture data with your Thank you.
One more question? Thank you. So if anyone needs to take a quick break, feel free to do that. The restrooms are directly outside. We'll come back in 5 minutes.